All right, we are talking about water again, and this is actually a topic that is uh, really kind of important, and somehow it's not covered terribly well in the textbook directly. I mean, they get to the issues of what hydrophilic and hydrophobic mean later on in the context of proteins and other structures and lipids, right? So in other words, these are terms that will be important to us later on, but the book never really stops and explains the difference between hydrophilic and hydrophobic and uh, how these differences, how this relates to the issue of covalent bonds. And that's what I'm going to do with this relatively short lecture. Okay, the reading appropriately would be 2.13, but that really does not cover completely what we need to get to. I mean, it talks about hydrophilic, but it really doesn't get to hydrophobic. We don't really see any mention of that until we get into the discussion of cellular membranes. Okay, and so our goal here is to get our minds around hydrophilic versus hydrophobic. And the context here is like we're right in the middle of discussion of water. We talked about how water has these properties that are totally conducive to the existence of life on Earth. I mean, life on Earth would be completely different if the oceans froze solid, for example. I mean, if solid water sank to the bottom, then we would have more or less perennially frozen oceans. That doesn't happen because ice flows, right? It comes to the surface, it's white, and so it reflects the incoming light, but it also creates an insulating layer over the liquid water below. So we don't get additional cooling of the water, and the oceans and lakes remain largely liquid underneath a thin shell of ice at the top, even during the coldest times of the year, right? The fact that water is really good at absorbing heat and really good at cooling and cohesive, and therefore able to be drawn up the vascular tissues of plants. I mean, these are all really kind of amazing features of water, properties of water that are due entirely to, remember, hydrogen bonds, right? H bonds are kind of like at the core of how we get to these amazing properties of water, right? We also, in the same context, we also talked about how our understanding of water as being a largely polar substance, right? H2O's got these two OH bonds, and we have a delta plus, very weak positive charge on the hydrogen ends of the water molecule. We've got a couple of negative charges on the oxygen side. And so the fact that every water molecule is this miniature three-dimensional magnet, right? It's kind of crazy, but it gives us not only these properties of water, but it also explains what kinds of things are going to be readily soluble in water, right? Things like ions, like a chloride ion having a negative charge is going to be forming these weak interactions, this weak dipole ion interaction with chloride, and that's going to be significant because ionic substances like sodium ion and chloride ion would be able to dissolve relatively easily in water. Okay? Not only that, I also drew a picture of how any substance is relatively small and has a significant number of polar covalent bonds, right? Small polar compounds like alcohols, like regular alcohol, stuff that is drinkable, right? If you are of an adequate age, is this molecule here. It's CH3CH2OH, or C2H6O. That would be the chemical formula here, right? 2 carbons, 6 hydrogens, and 1 oxygen, right? And this is ethanol. This is the one that's not going to kill you. I mean, could turn you into an addicted sot, but you're not going to die. I mean, in the previous time, the last time we talked about this, I drew a picture of methanol, which was just C, H, 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 and OH. And this is another alcohol that has got similar properties to ethanol, but this is one that you would not want to drink because it would actually kill you straight up. Right? And so different alcohols we're going to learn are all similar in having OH bonds inside of them, right? And so if we look at ethanol or methanol, these are both going to be water soluble. They're going to be water attracting because we've got a delta minus on the O side and delta plus on the H side. And these characteristics, these are the things that are going to cause water molecules to come in and form weak interactions with these structures, right? And so water molecules will be happy to interact with ethanol. They'll be happy to interact with methanol. They'll be happy to interact with either positively charged or negatively charged ions. Right? And so we've got through the first part, and it's all related to the fact that water is a polar substance with these OH bonds that have weak positive and weak negative charges. Right? And also, don't forget that we're talking about life on Earth. Life has evolved and unfolded in what's essentially a water-covered planet, right? I mean, it would be hard to imagine how living systems could take shape on a planet that was either absent of water, had no water, or had very little water. I mean, if we had a primarily dry planet, if life could evolve at all, it would have to take a completely different shape relative to what we have on Earth. So life as we know it has unfolded, has adapted, has emerged from what's largely a water-covered planet. And so water is really central to a lot of our discussions in biology. Okay? Now getting to the point, we've already kind of talked about this. Hydrophilic, literally, philic means loving. Hydro means water. You know that one. And so water-loving substance will be one that's hydrophilic. And these are things that are either going to be water-soluble, like sodium and chloride, Na plus Cl minus. That's the way you really should be depicting sodium chloride, table salt, even though we normally just say NaCl. Okay? Some people have even turned that into an acronym. They say NaCl. Okay? Personally, I don't like that too much, but NaCl is an ionic substance. We've got cations, sodium, and anions, chloride, that are forming this crystalline structure because the little positive and negative charges fit together really nicely and they form this regular block-like arrangement. Okay, but table salt is water soluble. Okay, because it breaks apart into ions. Right, if sodium chloride did not separate into single ions of chloride and single ions of sodium, then it would not be. There would be nothing there for water molecules to interact with, right? And so the fact that table salt is ionic, dissociating into single positively charged and negatively charged ions is what makes it water attracting or water loving, right? Ethanol, methanol, you would say, well, these are both substances that are hydrophilic because they have an OH structure on them. They're going to be polar to the extent that water molecules will have enough to be attracted to them, right? And so, yeah, hydrophilic means water loving, water soluble, or water attracting. It doesn't have to be water soluble. If you have something that's really large, like cellulose, it's a chemical that we'll be talking about later on. Cellulose it's got a lot of OHs, but it's a big molecule. It's this. You think of like a sheet of paper, right? A sheet of paper, regular old paper that you write on, would have layers and layers of microfibrils of cellulose, and the main structure of cellulose has got a whole bunch of OHs on it, right? There are lots of OHs on the general structure of cellulose, and this is why paper will absorb water, right? So water will come along here and it'll say, hey, that's a polar entity, and I'm going to be adhering to that. And water molecules will join in and they'll creep up. And the reason why paper is going to absorb water is because it's a hydrophilic substance. Right? Now, if you get that, now we can start thinking about what it means to be hydrophobic, right? Literally, phobos is fear. And so something that's hydrophobic would be water fearing, although that's not really an accurate depiction of what's happening, right? And but it's actually pretty easy to understand. If having a lot of OHs and NHs is what makes things like methanol and ethanol and cellulose hydrophilic, then the absence of any OHs and NHs would give us something that would not be able to attract water molecules. And if we don't attract water molecules, it's because we don't have any things like OH bonds or NH bonds or ionic charges. We don't have anything that would attract the water molecules. It's based on its chemical structure. Okay. And two, it would have to be something based entirely on nonpolar bonds. Okay. And these nonpolar bonds only are going to be the ones that are going to be either C, carbon, carbon, O, and CH bonds. Okay. And it's actually kind of fun to construct a molecule with C, and CH bonds because it's like putting together little blocks. You can say each C is going to be bonded to 4 things. Maybe you'll put another C over here, and it's already got 1 bond. Put structures like like that now, and then we could put maybe another C over here. It's got to be bonded to 4 things total. Okay, you could make this as big as you want. I mean, you could keep on adding more and more C's to the structure, but let's leave it the way it is right now. Okay. Now you can go through and add hydrogens to all the bonds that are not specified. And you'll realize, if you think about this for more than a minute, you'll realize that what I've drawn here is a perfectly good covalently bonded molecule, right? Because every C has 4 bonds, every H has 1 bond. We followed the rules perfectly, okay? And this is going to be completely absent of any polar covalent bonds. There's nothing here for water molecules to interact with, right? So here's a water molecule. Water molecule has its little delta minus charges, delta plus charges. But the water molecules are going to say, well, this guy over here, there's nothing for me to interact with on that structure. But I would be more than happy to interact with this water molecule over here because I've got a delta plus charge over here, delta plus charge over here on this hydrogen, delta minus charges on the oxygen. And so this water molecule, let me draw it in a different color, make sure you know what I'm identifying. This water molecule here, it has a choice. It could interact with the thing that I've drawn over on the left with only carbon and hydrogen, or it could interact with this water molecule. And every time it's going to interact with a water molecules like to interact with each other, but they kind of shun molecules like this guy on the left, which completely lack polar covalent bonds, right? There's nothing here for a water molecule to interact with, and that's why the water molecules don't interact with it. Okay? They would much rather hang out with other water molecules. Okay? This water molecule would be hanging out with another water molecule over here, and so you would end up with lots of water molecules that are fitting together and playing with each other, having brief attractions, and then moving on to the next water molecule. But nobody's going to be associating with our poor little nonpolar substance. excluded from the party because all the water molecules want to interact with each other. Okay. Okay, so I'm hoping that makes sense on kind of like a molecular basis, and we'll come back to our original picture here and say, yeah, our concept of hydrophobic literally means water-fearing, but maybe a better way of thinking about it would be water excluded, right? What we just described. And it's going to be composed either exclusively of nonpolar molecules or maybe nearly exclusively nonpolar compounds. If you have a very, very large molecule that's all carbons and hydrogens and maybe one little OH on it, okay? Yeah, technically that OH is going to be attracting water, but the entire rest of the molecule will be hydrophobic. And so overall, you would say that molecule is more hydrophobic than, and only in a very slight way, hydrophilic, right? And we will be, I'm not giving you that as a piece of meaningless trivia. We'll be looking at a molecule really soon that fits that bill entirely, right? I'm talking about cholesterol. When we get to cholesterol, I'm going to remind you about this and say, hey, yeah, this was an example of a molecule that is largely hydrophobic because you only have carbons and hydrogens. But look, way over here on this end of the molecule, you've got OH, and that's what makes it a little bit hydrophilic. Okay. Right. So the other thing we're going to be doing here is entirely practical, because part of your bag of tricks as a biologist, and you really are biologists this semester because you are in a biology class, you're gearing up to do lots more biology classes, Bio 220, 230, 210, maybe more beyond that, okay? And so part of your skill as a biologist would be to look at molecular structures and ascertain something about them, right? And so what I mean by this is that you can look at a molecule like this. So let me erase everything except for the first molecule that I drew. You can look at a molecule like this and say, hey, no OH bonds, no NH bonds, only carbons and hydrogens. This must be nonpolar and therefore hydrophobic. Okay. If you look at a piece of waxed paper, wax paper, you know what I'm talking about, which is basically paper that has been completely saturated with wax, and so you know that it does not absorb water, right? And so remember how I said that a sheet of paper is going to absorb water because water is going to be climbing up onto these OH structures on the water. Well, the OH structures of wax paper have been covered up with entirely non-polar hydrophobic substances. So if you were to look at the same sample of wax paper, yeah, here's the basic paper underneath all the wax, right? Then you put on top of that a waxy layer. So you got wax all the way around it, and there's no OHs on the outside of that. You put that into water molecules, right? Water molecules, H2O, are going to have nothing to interact with there, so they're not going to be attracted to it at all, right? It's not going to absorb any water because the water molecules have nothing to interact with on the wax paper. Something that is totally greasy, okay, like oils, fats, right? You know what I'm talking about. Greasy substances don't mix with water, right? Oil and water don't mix. If you put them into a cup, okay, if you've never done this, you have a glass of water, you put some vegetable oil in, vegetable oil floats to the surface and does not mix with the water. Why does it not mix with the water? Well, it's because vegetable oil is entirely nonpolar. And so things that are either greasy, not mixing with water, hydrophobic, not absorbing water, the characteristic of these molecules are that they lack the OHs and the NHs, have only CHs in their structure. And that's an easy way of looking at a molecule, looking at a chemical structure and saying, hey, that's hydrophobic. That's going to be non-water absorbing, non-water soluble. It's entirely nonpolar. Okay? Conversely, if you were to look at, oh God, to select. Okay, okay, if you were to look at a molecule like this is a molecule we will actually draw, learn to draw. Okay, I'm actually drawing a legitimate molecule for you. This is glucose. You are metabolizing bazillions of molecules of glucose. This very second. Your cells are taking glucose and consuming it, converting it into carbon dioxide and water to in the whole process of keeping your body from running out of energy, right? So yeah, this is a legitimate molecule, and not too long from now, next week, you will be looking at a molecule like this and saying, hey, I need to figure out what kind of molecule this is, okay? And so we're going to be going through the steps of how to recognize molecules that belong to the carbohydrate class. Yeah, you have carbon and H2O, carbohydrate, in about the ratios of 1C for every 2 H's for every 1 oxygen. And if you look at the molecule of glucose here, there are exactly 6 carbons, there are 12 hydrogens, and there are 6 oxygens. And so you're going to be learning how to recognize molecules. And this is one of the skills that I do want you to develop as a result of coming through my class. Okay. But for right now, okay, what I would expect you to be able to do right now is to look at this molecule and tell me whether it's polar or nonpolar. Can you do that? Okay. Now hopefully you said, okay, well, I know that OH bonds are polar, and I've got an OH bond here. That means I'm going to have a delta negative over here, delta positive over here, delta negative, delta positive, delta negative, delta positive. So I guess the question is this going to be a structure that will be attractive to water molecules? And the answer has got to be yes, right? This is going to be a polar substance, it's going to be water attractive. And so you would expect sugars and carbohydrates generally to be water soluble or hydrophilic. Okay. So yeah, I mean, easy thing, you look for OHs. You look alternatively for NHs. If you have got a lot of NHs on there, those are going to be points in which water molecules will be interacting. Okay? If you don't see any things that would be polar or nonpolar, say no OHs, no NHs, then you could draw the conclusion that what we're looking at is a molecule that would be hydrophobic because of the nonpolar molecular structure. Okay. And I think we've done this entirely. Talked about how nonpolar molecules are going to be hydrophobic. You can recognize hydrophilic / polar from hydrophobic / nonpolar based on the presence, absence of structures that would be attractive to water, right? Not only do we have OHs and NHs SH, sulfur, is actually has very similar properties to oxygen, and so sulfur hydro, a sulfhydryl group SH would be delta negative on the S side, delta positive on the H side, very similar to the way, similarly to how you have polarity in water in OH groups, right? Also, if you have something that, if you have, let me move over here. Okay. If you had this molecule, but instead of a hydrogen there, if you were to have a phosphate group, O, P, O, 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 okay? And so if we have a phosphate group where you've got a negative charge here, a full-on negative charge, not a delta negative charge, not a weaker version. Not only do we have one, we've got two full-on ionic charges here. Right? This would be PO4 2 minus. There's actually a double charge on this phosphate group, right? Yeah, totally. This would be a structure in which water molecules will be interacting, right? OH, okay? Delta minus, delta plus, and so you'd have that same dipole ion interaction in the presence of an entity, structural entity on the molecule that would cause it to have a charge. Okay? So yeah, I mean, the rest of the molecule might be largely hydrophobic, a hydrocarbon, but because of the phosphate group, it's going to be highly water attracting, at least the part of the molecule that will be there with the phosphate group. Okay. The one thing I think we can just clarify right now, the word hydrocarbon is a pretty self-explanatory thing. If you have a molecule that consists only of carbon and hydrogen, okay, one, it would be absent of polar bonds, it would be hydrophobic, and it will also be in the class of hydrocarbons. Okay? So for example, the molecule that we looked at before, methane, has only carbons and hydrogens. It would be a hydrocarbon. You can make a molecule like the one that we drew on the other board. And you could fill in the H's here if you like. My sketch pad is kind of slow. It's got a little bit of lag, which is why all of my H's are not looking like H's. If you have only C's and H's, you know that it's nonpolar and it's going to be greasy. It's not going to mix with water. Well, you would also be able to recognize these molecules A and B as being belonging to the class of molecules that are known as hydrocarbons. Okay. Now, very briefly, I want to make sure that you guys are looking at the thing that we're talking about. Water is the solvent of life. And as we scroll through this, it just kind of, in a very sketchy way, talks about how molecules of water are interacting with sodium ions and chloride ions. We talked about this in the lecture, but it also kind of talks about the general feature of water being a polar solvent and able to dissolve things that are polar and or charged, which is kind of like the very first step that you would need to have in order to appreciate today's lecture. All right, that's it for now.